Let's take a look at a quotient of a Boolean algebra. We're going to be looking at a particular Boolean algebra, the power set of a set S, where the size of S is 3, and we're going to be thinking about subset codes. Now, we're going to use this notation right here to mean that all subsets that lie below this one. So this right here is a subset code. So 3 different elements. This means take just the first element. So this is just a set with just one thing in it. And this means take all subsets of it, or anything that lies below it. Well, there's only one thing that lies below it, the empty set. Okay, so basically we're going to be quotienting out this Boolean algebra by this in what kind of a way? Well, we can think about our Boolean algebra as being a ring with respect to an operation which we can call the symmetric difference, but I'll just notate it like this. So it's some kind of addition. I put a little swivel underneath. But really, this addition, if you look at it, the symmetric difference means that if you take so if you take two sets, two subsets of this, so say you have something like 0, 1, 1. So pretty much what you're doing is you're taking the union of these two guys and then throwing out what's common. So what's common is right here, so we're going to be throwing that out and then taking the union of what's left over. And so that would be 1, 0, 1. But notice it can also be obtained simply by adding mod 2, if you will, component-wise. 1, 0, 1. Just for each component, mod 2. Arithmetic. So really it's just addition mod 2 arithmetic on these subset codes component wise. Thinking about B being a Boolean algebra as simply being z mod 2z cross z mod 2z cross z mod 2z. So we're taking tuples in ones and zeros, but that's exactly what we're doing with subset codes. Okay, so we just basically have addition here, all right? So we're quotienting out the Boolean algebra by a subgroup. So this is actually a subgroup with respect to this addition. You think about it, yeah, you add these things. You're not going to get out of this set by doing this particular addition. You're going to be sticking here. So this is a subgroup. So this is, and B is a group, an additive group with respect to this, and we're taking a group quotient, you could say. But it's more than that. This group quotient is actually a ring quotient. Wow, so the Boolean algebra has a ring structure. It does. The Boolean algebra, we can see, has an addition structure, but it also has a multiplication structure, namely taking intersections. So if we intersect two things, like let's suppose we want to intersect these two guys right here, their intersection is so 1, 1, 0, 0, 1, 1, and we intersect. The intersection is just 0, 1, 0. But notice you can get this just by multiplying right here. 1 times 0 is 0, 1 times 1 is 1, 0 times 1 is 0. And it behaves very well across this addition. It turns it into a ring. And this guy right here is actually an ideal. It's not just a subgroup with respect to this, but if we were to intersect anything at all in the Boolean algebra, in this power set, to anything in this group, we'd be in that group. Because you think about it, you intersect, you're going to be inside of whatever you're here in, and we're always going to be inside of 1, 0, 0. And so we're going to be a subset of it if we intersect with it. It means it's closed under like outside multiplication by other elements in the Boolean algebra. So this makes the Boolean algebra into a nice ring, and this is actually a ring quotient. Then this ring quotient is great because these operations of meet and join, or and or, if you will, are actually completely expressible in terms of this plus and this multiplication right here, and this quotient structure produces chunks that in such a way, so it produces chunks out of the out of all the subsets, kind of groups them into pieces, into cosets, additive shifts of this guy in such a way that, you know what, if you that we have this nice operation of meet and join between the chunks, not only plus and multiply as you usually do in a ring quotient, but you also have these guys too acting well between them, such that if you take any, so for instance, if you take anything in, let's just look at an example of that here to kind of see what that looks like. For instance, well, if we have a chunk like 1, 0, 1, okay, and I'll put a bar for, everything in that chunk, and we have something, right, and let's just extend it over, and let's say we're taking a join with maybe like 0, 1, 0, right? Now, this right here, we can actually think about, so what does it mean for the operation to be preserved in this merging process in this quotient? It means we can, if we do this operation before or after, you should get the same result. Namely, something like this, the bar can actually split all across the operation, and then you could even like change the representative here, change the representative here, and then throw the bar back over and end up getting the exact same thing again. And let's actually see how that works once we find out what these additive shifts really are, what these cosets are here. So how do we do that? How do we find the additive shifts of that guy with this? Well, we already know what this is. It's this set. So let's just get some shifts of it, all right? So we have this one. So we have one, this is the subgroup or the ideal. We call it an ideal because it's closed with respect to this multiplication. So we have 0, 0, 0, 1, 0, 0 in this ideal. Let's look at a shift of it. If we were to add, think mod 2 arithmetic, which is the same thing as the symmetric difference operation. So let's just add different things to this to get different sets, all right, until we partition all of this power set into chunks. So what if we added by maybe like, so we take this and we add with this operation like by 0, 1, 0, what would happen? So you add this to both of those guys and you get 0, 1, 0, 1, 1, 0. Okay, so that's a chunk. All right, so now let's take this and add by something else, something that we don't already have, maybe like by this guy. So if we add by that, then we end up getting a chunk. Let's see, 0, 1, 1, and 1, 1, 1. Okay, now let's pick something that we don't have currently here. What about 0? Let's see, we don't have 0, 0, 1 yet, do we? 0, 0, 1. Okay, so let's add both things by 0, 0, 1. So then we're going to get 0, 0, 1 and 1, 0, 1, and notice that we have 8 different subset codes going on, so which is all we have for this power set. We have 8 subsets of S, so therefore we've partitioned it, and these are the different chunks. Okay, so we have these different chunks happening here. So using this idea, let's go back over here and see kind of what we can do. Can we really replace this by another representative of this chunk and still get the same result? Doing so, let's see what we got here. If we get, okay, so 1, 0, 1, that is in this one. Let's replace it with 0, 0, 1. 0, 0, 1. Okay, all right, let's just replace that one, all right? And so then we have, so we can replace this with this, and then we're still joining on with this guy, but let's throw the bar over everything. And take the join of these, and you notice, or the union, if you will, and you'll get 0, 1, 1. So this is going to be 0, 1, 1 bar. Okay. Okay, so 0, 1, 1 bar. And let's look what chunk that lies in. Oh, it lies in this chunk right here. Okay. Well, that's exactly what we should expect if we did the operation first over here. Because then that would be 1, 1, 1 bar. And notice that 1, 1, 1 bar is the same thing as 0, 1, 1 bar. They're the exact same chunk. Okay, so it behaves nicely. We have this nice ring structure with this addition and with this multiplication, and we've determined different cosets or shifts of this ideal right here, and that these are the chunks that make up this particular Boolean algebra. And we can take a look and see what those chunks look like in a picture. They look like this. Okay, so this chunk, this chunk, and so forth. And this merging process is also preserves poset structure as well. And so you can kind of think of, so we have a chunk here. So we have a chunk right here, we have a chunk here, here, and here. And there's arrows like that, and so you have an arrow. So this chunk right here actually goes to that one and that one. So and this is just a Hasse diagram anyhow. So but you really have this an arrow going up here in the poset by transitivity and all around. But this is the new Boolean algebra that we get by chunking. So yes, the ring that we get is a ring. The ring quotient of that will again be a Boolean algebra. In fact, if you think about it, we were looking at z mod 2z to the third, or like this Cartesian product with 3 components, and we're modding out essentially by one of these components. That one. We're modding out by that one, kind of zeroing out, pretending like it's 0. And what we end up getting is z mod 2z, which actually has the same structure again, with that plus symmetric difference and the multiplication. In another video, I actually demonstrate how regular union and is obtained from these operations, natural ring operations that we have here, just with multiplication component-wise, as well and addition in mod 2. We can actually extrapolate that or get that out of it to turn into to give us regular union as well. Okay, so that was just a little example of how we can have a ring structure and quotient get into chunks within a Boolean algebra that preserves unions and intersections, or joins and meets, and also the operations of symmetric difference and meet. Okay, thanks for watching.